All right, diving in again. This time we're looking at electricity and electronics.
Yeah, we're going deep with this one.
Got our teacher guides and revision sheets ready so you know we're getting into the nitty-gritty. But this isn't just about remembering Ohm's law from school.
Right. We're going to try to get to those real aha moments.
Exactly, like suddenly understanding how those tiny charges in a wire can also create something as powerful as lightning.
Yeah, or like how all those little electrons actually power all the devices we rely on.
Totally. Even peeking into the logic that drives our smartphones. I mean, that's pretty amazing stuff.
Definitely.
Okay, so got to start with the fundamentals, right? Electrical charge. I think everyone knows that feeling,
Oh, yeah.
that static shock when you touch a doorknob
Yeah.
after shuffling across the carpet. That's electrical charge, right? But what's actually going on there?
So basically, it's all about these two types of charge, positive and negative. They're always interacting. It's kind of like magnets, you know?
Oh, yeah.
Opposite charges attract and like charges repel.
Ah, that makes sense.
And this, even though it seems so simple, it's actually behind some of the most powerful forces we know.
Really?
Yeah, like lightning
Oh, wow.
or the circuits that power, well, pretty
Yeah.
much everything around us.
It's all about how those charges react to each other.
Exactly.
That's how we actually get the energy we use, right?
Yeah, and that brings us to current and voltage.
Okay.
Current is basically the flow of those charges,
Okay.
those tiny electrons,
Yeah.
zipping through a wire.
Uh-huh.
Think of it like cars on a highway.
Okay, yeah.
And we measure that flow in amperes or amps. It's like a speedometer for electrons.
So current is the movement, the flow of those electrons.
Exactly.
But something has to be pushing that flow along. That's where voltage comes in, right?
You got it. Voltage is the force that's pushing those electrons along.
Right.
Imagine a water pipe, right? The higher the pressure, the faster the water flows.
Oh, okay.
So voltage is like that pressure driving the current.
Makes sense.
We measure it in volts.
Okay.
And like we use a pressure gauge for water, we use a voltmeter for this electrical pressure.
Ah, okay. So we've got electrons flowing as current, pushed by that force of voltage.
Right.
But how does all of this actually translate to the circuits, the actual things that power everything around us?
Well, there are two main types of circuits, series and parallel.
Okay.
A series circuit is like, think of it as a single lane road.
Okay.
The current only has one path to follow.
Right.
If there's any blockage anywhere along that path, the entire flow just stops.
Like those old Christmas lights.
Exactly.
If one bulb went out, the whole string went dark. That was a series circuit.
Exactly. Now think of a multi-lane highway.
Okay.
That's a parallel circuit.
Uh,
Current can take multiple paths, so even if one lane, so to speak, gets blocked, the flow can still continue.
so that's how the wiring in our houses works.
Exactly.
That's why one light going out doesn't shut down the whole house.
Exactly. But the way current and voltage act in those circuits, it's kind of interesting.
Oh, how so?
So in a series circuit, the current, it stays the same all the way through that loop. Like
yeah.
that single lane road, you know, the same number of cars passing a certain point every minute.
Right.
But the voltage is shared across all the different components.
Okay, so each component is getting a portion of that total voltage,
Precisely.
like splitting a pie.
Yeah, like splitting a pie.
The more pieces, the smaller the slices.
Exactly. Now, in a parallel circuit, each branch, it gets the full voltage.
Really?
Yeah, it's like having multiple faucets hooked up to the same water main. Each faucet is getting that same water pressure.
Oh, okay, I get it. So voltage stays the same in each branch of the parallel circuit.
Right.
What about current?
In a parallel circuit, the total current from the source, it gets divided between all the branches.
Okay.
Each branch is taking a part of that total current.
So the more branches you add, the more that total current gets split up.
Exactly.
It's really amazing how all of this works so predictably. It's like there are these rules that govern how electricity flows.
Yeah.
But how do we actually use this flow to make something, useful? It's more than just wires and a power source, right?
Absolutely. And that's where electronic systems come in.
Okay.
Every electronic system, whether it's something simple like a flashlight or something as complex as a computer,
Right.
it's all built on three things: input, process, and output.
That's interesting. It almost sounds like a biological system or something.
It kind of is.
Like our bodies, our senses take input, then our brains process that information,
Right.
and then our muscles do something, the output, based on what our brains processed.
Exact.
Is that a fair comparison?
It is. So take a microphone, for example.
Okay.
The sound waves, That's the input. They hit the
Yeah.
diaphragm,
Uh-huh.
and that converts that mechanical energy into electrical signals.
Okay.
Then those signals get processed, maybe they're amplified or filtered, and finally, they're sent to a speaker, the output.
Okay.
And that turns them back into sound waves that we can hear.
So we're taking energy from the world around us, turning it into electrical signals, then processing those signals,
Yes.
and then turning those signals back into a different kind of energy to, well, do something.
Right.
That's wild.
And a really key part of that processing stage are logic gates.
Oh, right.
Do you remember those?
Yeah. The tiny electrical decision makers,
Exactly.
like the brains of our electronic systems,
Oh,
right?
exactly. Logic gates make decisions based on those input signals they get,
Yeah.
and that determines what the output's going to be.
Sure.
They're basically the building blocks of how we get electronics to compute and to control things.
So how do those actually work? What
Yeah.
kinds of decisions can they make?
Well, there are quite a few types, but let's just focus on 3 basic ones for now.
Okay.
Not, needy, AD, and OR gates.
Okay, I'm intrigued. Let's
Yeah.
break it down. What's a NOT gate do?
A NOT gate, that's the simplest one. It just inverts the input signal.
What does that mean?
So if the input is on, the output will be off, and vice versa.
So it's like a reverse switch. If the input says go, the NOT gate says stop.
Exactly.
What about AND gates? How do those work?
An AND gate needs both of its inputs to be on for the output to be on.
Oh, okay.
If even one input is off, the output will be off too.
So both things have to be true for it to work.
Exactly.
What about OR gates?
An OR gate is a little more, well, lenient. It will give you an on output if at least one of its inputs is on.
Okay.
Only if both inputs are off, will the output also be off.
So it's like having 2 light switches to control one light. You can flip either switch on to light up the room.
Exactly.
It seems like just these 3 simple types of gates could be combined to make some pretty complex decisions.
You are absolutely right. These are the foundation of everything, from simple timers
Wow.
to the complex calculations going on inside your smartphone.
That's incredible. It's amazing how such basic things can lead to such complex systems. I can't wait to see how these are actually used in the real world.
Me too. It's fascinating how we can go from these building blocks to the technology that shapes our world.
Yeah. I'm already thinking about my phone differently.
I know, right?
All right, well, let's dive even deeper next time.
Let's do it. So we've got those basic logic gates, not T, AND, and OR. But how do we go from those simple things to something as complex as, like, a computer?
That's what always gets me. It's like, how do you go from individual bricks to a whole skyscraper?
It's a good analogy, and it is like building a skyscraper. It's all about combining those basic elements in, well, more and more complex ways.
Okay.
With logic gates, we can build circuits that can do specific tasks,
Right.
make decisions based on different conditions,
Uh-huh.
even store information.
Okay, so it's about connecting those logic gates together in the right way. Can you give me an example? How would that work?
Sure. Let's say you want to design a system to control a sprinkler system based on the weather.
Okay, yeah.
We could use a moisture sensor in the ground as one input.
Okay.
So if the soil is dry, the sensor sends an on signal.
So that's our first condition. Dry soil means the plants need water. What else?
We also don't want those sprinklers going off if it's raining.
Right, of course.
So we could use a rain sensor for another input.
Okay.
If it's raining, that sensor sends an on signal,
Okay, so now we have 2 inputs.
right?
One tells us if the soil is dry. The other tells us if it's raining.
Exactly.
How do we use those to decide about the sprinklers?
That's where those logic gates come in.
Okay.
We want those sprinklers to turn on only if the soil is dry and it's not raining. So which gate should we use?
We need both things to be true, so it sounds like an AND gate.
Right. Got it.
But wait, the rain sensor sends an on signal when it's raining. Wouldn't that make the AND gate turn on the sprinklers?
You're right. To fix that, we can add a not T gate.
Oh, okay.
We connect the rain sensor's output to the not T gate.
So if it is raining,
Yet the sensor sends the on signal, but the not gate flips it to off.
oh, that's clever. So now, even when it's raining,
Right.
the output from the NOT gate will be off.
Exactly.
So the AND gate will only turn on if the soil is also dry.
Exactly. So we connect the moisture sensor's output and the NOT gate's output to the AND gate's inputs.
Okay.
The AND gate will only send an on signal to turn on those sprinklers if the soil is dry, meaning the moisture sensor's on,
Right.
and it's not raining, meaning the rain sensor's on has been flipped to off by that NOT gate.
Wow. So with just a couple of sensors, a NOT gate
Mhm.
and an A&D gate, we've built a pretty smart system.
Right.
It can control our sprinklers based on the actual weather.
Exactly.
It's amazing how these simple pieces can do something so complex.
And that's just a taste of what's possible. If you combine more logic gates, you can create circuits that can make really complex decisions.
Wow.
They can process information from lots of different sources
Okay.
and control a whole bunch of different things.
So how do we get from circuits like this to the chips in our computers and phones? That seems like a huge jump.
It is a big jump, yeah, but the basic ideas are the same. The trick is miniaturization and integration.
What does that mean?
Instead of building these circuits with separate parts, we can make them super small, super intricate, right on tiny pieces of silicon.
Oh, okay. Like microchips.
Exactly.
So instead of having individual wires and components, we're talking about etching those pathways and things directly onto a chip.
Yeah, and the key to doing all that is the transistor.
Oh, right. We talked about those before. They replaced those old vacuum tubes,
Yeah.
right? But how do transistors fit into this whole thing with logic gates and chips?
Transistors are basically tiny switches.
Okay,
They control the flow of current based on an input signal.
right.
They're like the fundamental building blocks for making logic gates. Each logic gate is made with a specific arrangement of transistors.
So instead of having these big clunky switches, we're using these microscopic transistors
Yeah.
to do the switching for those logic gates.
Right.
And we can fit billions of those transistors onto a single chip.
Exactly. And that's how we get from those simple logic gates to the super complex integrated circuits, the heart of our computers and smartphones.
It's mind-blowing to think about how small and how complex those chips are. It's like having whole cities of those interconnected logic gates
It is.
all working together super fast.
And it all comes from those basic ideas we've been talking about,
Right.
electrical charge, current, voltage, and the logic of those gates. It's pretty amazing what we've been able to do with that stuff.
It really is.
Yeah.
But these systems don't just exist on their own, do they?
No.
They have to interact with the actual world
Yeah.
to actually be useful.
Right.
And that brings us back to input and output devices, I guess.
Exactly. Input devices are how we connect the physical world to that electronic world.
Right.
They take different kinds of energy, light, sound, pressure, motion, and turn it into electrical signals that our electronics can understand.
So things like microphones, cameras, keyboards, touchscreens,
All of that.
those are all input devices.
Yeah.
They take information from the real world and translate it.
Right.
What about output devices?
Yeah.
How do they complete the loop?
Output devices do the opposite.
Okay.
They take the electrical signals from those systems and turn them back into something that we can see, hear, or feel, something that can interact with the real world.
So things like speakers, displays, motors, actuators, all that.
Exactly. Think about a digital thermometer. A temperature sensor, that's the input. It converts temperature into an electrical signal.
Okay.
The electronics process that signal, turn it into a digital reading,
Right.
and then the display, the output, shows us that temperature.
It's amazing how smoothly those input, process, and output stages work together. It makes you really think about what's going on inside all these devices.
It is, and that's just a peek into the world of electronics as technology keeps getting better. Who knows what amazing new stuff we'll be able to build using these same ideas.
I can't wait to find out. But before we go too far, let's take a look at some real-world examples of how these logic gates and systems actually work.
Sounds good.
We've gone from those tiny electrons all the way to these microchips packed with billions of transistors.
Yeah, it's been quite a journey.
But I'm really curious to see how all of this actually works in the things we use every day.
Well, let's take something we all have.
Yep.
A simple home security system.
Right.
It's a great example of how those input devices, logic gates, and output devices all work together.
Okay, I'm thinking about those sensors on the doors and windows.
Right?
The keypad to arm and disarm the system.
Yep.
And that siren that goes off if there's a break-in.
Exactly. Those sensors on your doors and windows, those are your input devices.
Okay.
So when a door or window opens, there's a magnetic contact in the sensor, it breaks, and that sends an on signal to the control panel.
So that signals like a tripwire, tells the system that something's happening.
Yeah.
So where do the logic gates come in?
The logic gates in that control panel, they're programmed to make decisions
Okay,
based on the signals they're getting.
right.
So, for example, if the system is armed, AMD, a door sensor, sends an on signal.
Okay.
The A&D gate triggers the siren.
So the A&D gate makes sure the alarm only goes off if the system is armed. A&D, a sensor, has been triggered.
Right.
That's smart. That stops it from going off if you just accidentally left a door open.
Exactly. Now, let's say you want to get a little more fancy. Lots of systems let you set up different zones.
Okay, yeah.
You might want the downstairs sensors on at night, but not the ones upstairs.
Right, right. So how do you do that kind of zone control with those logic gates?
That's where those OR gates come in handy.
Okay,
Let's say you use the keypad to arm just the downstairs zone.
all right.
That sends an on signal to an OR gate. Now, that OR gate will trigger the alarm if either the downstairs sensors are tripped or the whole system is armed.
So even if I don't arm the whole system, the downstairs zone could still trigger the alarm.
Exactly.
That's pretty cool. You can use logic to make the system really flexible.
And that's just a simple example. Those modern systems use a whole network of logic gates
Really?
to handle different zones, time-based arming, you name it. It's really amazing what you can do with those simple logic elements.
It really is. It's like all those tiny transistors and logic gates are running the show behind the scenes. Changes how you think about these things.
And it's the same kind of logic in a ton of other devices we use every day.
Oh, yeah. Like what?
Your thermostat.
Okay.
It uses logic gates to compare the current temperature to what you set it to.
Right.
And then it controls the heating or cooling. Your microwave uses them to manage the timing and power levels.
It's everywhere. Even our cars.
Exactly.
All that stuff with the engine, the brakes, it's all input signals, processing, output commands.
It all comes back to those basic ideas we've been talking about. From charges to logic gates, it's amazing how it all comes together to create the tech that we use every single day.
This deep dive has really been eye-opening. I'm never going to look at my electronics the same way again.
That's the power of understanding how things actually work. You start to appreciate all the incredible stuff that's happening all the time.
So anyone out there who thought electronics were just a bunch of wires, I hope this showed you how elegant and powerful these ideas really are.
And as tech keeps advancing, it's only going to get more important to understand these building blocks.
That's true. Who knows what's coming next?
Exactly.
Well, that's all the time we have for this deep dive. But keep exploring, keep learning, and we'll see you next time.